So it is our pleasure to have today in IAP Katia Matcheva, who is an associate professor at the University of Florida in Gainesville. I know Katia for a long time because after her thesis with Darrell Strobel in planetology and Jupiter gravity waves observed by the Galileo probe, she worked in ESA in Paris Observatory with me on the gravity waves and relation with H3+ emission. And then she moved from planetology recently to artificial intelligence programs and machine learning in the Department of Physics of Florida. And she works with Konstantin Matcheva, who's present here too, who is professor there in the same domain. And Katia will explain this new field and how she works on that today. Thank you, Katia.
Thanks, Pierre. Can everybody hear me? Yes, we have a mic? Great. I hope the Zoom meeting also can hear me. If there are questions on Zoom, I wouldn't be able to see you. So hopefully you can always interrupt and ask a question. Feel free to do so. Okay. Well, I feel almost home, especially I have a bamboo stick and I have in my yard in Florida a big bamboo, and that feels very much like at home. As a matter of fact, in our physics department, in our seminar room, we also have a bamboo stick. Some Floridians here already know. So I do feel very much at home. So today, I'd like to talk about the application of machine learning and the so-called AI for exploration of extrasolar system planets. And this is a work that my group does together with Konstantin and a few students, graduate students at the University of Florida. So we are known as the Gators. This is why we have the logo. Let's see, are we moving? We're frozen. Let's see what's going on. Oh, there you go, we moved. Okay, so this is my research group, as a matter of fact. You can see on the background a very nice representation of Florida spring weather, actually winter spring weather, very sunny. You're very much welcome to visit Florida anytime. I have Konstantin and myself and our 3 graduate students. One of them actually graduated this spring. And all of them work on application of machine learning techniques for a variety of physics problems, not only exoplanets, but machine learning techniques and AI on particle physics problems. We have a few papers on that, and also mathematical physics. That's to show that there is a very interdisciplinary application of machine learning techniques in a variety of physics settings. So, yes, we're known as the Gators, and this is the famous, now famous diagram that shows emphasizes the interdisciplinary character of using machine learning in a variety of fields. You need to have the hacking skills, you need to have the statistical, mathematical skills, but you also, very importantly, need to have the domain knowledge in the field that you want to apply those tools. So our group is a very perfect combination of those, with excellent programming skills that the students have, mathematical and statistical skills that Konstantin has in his pocket, and me as an expertise on planets and exoplanetary systems. So here we are. Today, I will first introduce a little bit about transmission spectroscopy, the main thing that we are applying machine learning in terms of exoplanets. And then I will give you some examples of a variety of applications of machine learning techniques in terms of supervised learning, unsupervised learning, symbolic regression, and all those different terms that are being used for applications in exoplanets. Okay, and at the end, I'm going to show you some examples of how we're searching for unusual planets, and maybe why not extraterrestrial life on other worlds by using anomaly detection and novelty detection techniques. So here we are, the standard video that is for illustrating the idea about transmission spectroscopy of transiting planets. When we have a planet that is far, far away. Keep in mind the geometry of the problem. We have stars far, far away, and we have planets far, far away that are going in front of the face of the star along the line of sight. So what we observe is the planet blocks a fraction of the stellar light that the instruments see, and by that we have a drop in the flux, stellar flux that is being observed. So right here, this drop is known as the dip of the light curve, and we're going to be discussing basically the magnitude of that dip that it goes in front. So basically, this is what you observe, and you can observe that at different wavelengths. And when you do that at different wavelengths, voila, you're going to have an actual spectrum. And this is what we call a spectrum during a transit of a planet that goes in front of the star. This is a primary transit, and we basically see it in flipped. And that particular curve, this kind of curve, as a function of, this is absorption or absorption or refraction, scattering through the atmosphere of the planet, of the stellar light at different wavelengths. Of course, we have here visible colors, but typically that's observed in the infrared. So we have that infrared spectrum that is observed of the star. Okay, so what do we use? We use a variety of, I mean, not me personally, but what scientists do use, variety of ground-based observations, but most importantly, a few space missions that have contributed to majority of the transmission spectroscopy that is being done on exoplanets. So the historical contribution of the Hubble Space Telescope that's I think in the 2009 had a very successful camera installed on it, the so-called Wild Field Camera 3 that does very nice infrared observations. And it has done more than, I mean, I think close to 40 or so spectral observation on transiting planets. We have currently the star of the space observations, the James Webb Telescope, that is very successfully observing planets in transmission in the infrared. And we're going to talk quite a lot about the upcoming star in our planetary observation, the Ariel mission. And of course, France has a significant contribution to that mission. So we're going to focus also on that. Here now, let's compare the specifications in terms of exoplanetary observations of those three missions. Here we have the traditional Hubble observation for spectra of a planet. This is just a representative spectra for one of the exoplanets right there. It has a phone number or license plate, whatever you like to call it. And what you can see is the observation is done between 0.5 and 1.7 microns. This is in the near infrared. And it has, depending how you average the individual beams, you have anywhere between 10 to 13 or 15 different channels, infrared channels that you observe that of spectral beams. So this was the state of the art in terms of space observation of transmission spectra. And this diagram actually shows, this is as of a year ago. So this is before James Webb launch. It was showing what is the fraction of the available transmission spectra from exoplanets, depending on which instrument is being used to see. So this big bite of the pie chart is actually the fraction of observation done with that particular camera of the Hubble Space Telescope. So you can see it has been the workhorse of all the observations. Now, note the spectral range right here. It looks big, but it's just from 0.5 to 1.7 or so microns. And we're moving here to James Webb, which is the star of the current observations. We have 4 different instruments in the infrared, from the near to the mid-infrared, and they're represented here. This is taken from the NASA website. And here with the red, I have marked right here, this is the spectral range of Hubble. So you can see what big jump of spectral coverage we have with this new addition, with new capabilities of JWST. Okay, so let's compare James W with the upcoming observations coming from the Ariel, the European space mission that will be has a plans to observe roughly about 1,000 different exoplanets in transmission. And how does that compare spectrally? Here you have the red that compares the spectral window of Hubble, and the green compares the spectral window of JW with respect to Ariel. So Ariel has even further expanded its spectral range. In addition, it has a plan or the ambition to remarkably increase the number of spectra, the number of planets that will be observed. So we're jumping from a few tens to 1,000 planets. And that is going to be a key to the argument why we should employ machine learning techniques in studying planets, because I'll show you that in a minute. The new challenges: 1,000 planets, 1,000 new worlds, 1,000 new PhDs. That's a lot. This is a lot. If you think about it, it's a lot of new information. We have to become smart or smarter. How we look at the data, how we analyze the data, how we search through the data, how we mark planets for further investigation. And this is what really starts motivating, looking for new techniques, whether they're faster, whether they're more precise, whether they're, how do we analyze that data so we most efficiently extract the information we need. So this is me with the longer hair. I'm joking. All right. So how actually did I get into that? So I was just discussing with Pierre that just around 2020, the University of Florida, in addition to the very dark times with the pandemic, all of a sudden we decided, the University of Florida decided to invest in a very big expansion in announcements for artificial intelligence initiative. The whole university, the whole campus, all the departments started expanding in this area, hiring new faculty, new researchers, adding to the facilities of the universities. We have major donations from NVIDIA in terms of computation. Our hypergator, get it? Our hypergator has a very remarkable capabilities nowadays, has been revamped with GPUs that were donated by NVIDIA. So our gator, now just to show you, our gator now is gator with an AR in the middle, okay, to emphasize the application of AI in a variety of different disciplines, from medical imaging, from data analysis, for statistics, for you name it. Every single department currently has, and every single undergraduate and graduate program has a class of machine learning, artificial intelligence applications, so to start to incorporate that in the curriculum of undergraduate education and PhD education. So it's a major initiative. And this is just about the time, I think it was in 2020 in the summer, when I started with a couple of new graduate students, and I was just about to go on a summer break, and I needed a project for them. And this is the time when we saw that there is a competition, the Ariel mission competition on data challenge for using machine learning techniques for analyzing the transmission spectra of future observations with Ariel. So what the best place to start with than having your students working on a competition? So we had our graduate students, the two of them, working together to learn about exoplanets, learn about spectra, and to enter the competition. And this is the way you enter the competition as a summer project. We were very competitive apparently, and we finished in the first place in the 2022 competition, and this year we are second behind the Harvard group in the 2023 competition. So as a matter of fact, we are on our way to the meeting that the Ariel mission is going to have in Hungary this next week, and we're going to be discussing some other things there. All right, so what do we learn from the spectroscopic observations? besides the fact that the light drops, as the light from the star passes through the atmosphere, which is this is a exaggeration in that figure, a very thin envelope for a terrestrial type planet and a very thick envelope for a giant planet. And as this light goes through the atmosphere, the light gets absorbed or scattered by the molecules present in the atmosphere or by the particulates present in the atmosphere, whether those are molecules or clouds or hazes, all those things interact with the light. And this is what contributes to the extinction of lights, of the starlights that go through the atmosphere. This is what causes the signature and the specific spectral signature that we see in those things. We see something like that. So this is, you see a representation of 3 different spectral signatures for from the transmitted stellar light. This flat one basically corresponds to something that is very, very cloudy or maybe no atmosphere at all. That means it has no much of a spectral modulation observed along the wavelengths. This one is representative for a water-dominated absorption. This one here, the red one is HCN, and here the green one is ammonia rich. It just tells you that you're going to have different spectral signature depending on the present molecules in the atmosphere. And this is basically the main goal of the spectroscopy, to learn about the composition and the structure of the atmosphere. One can have a general analytical expression for that. The analytical expression does have significant simplification. That's why you can have analytical expression. So with the analytical expression, you can see generally how the observed spectral signature depends on a variety of planetary parameters. You get a sense of what is impacting the observed stellar flux. It basically depends on the radius of the planet, radius of the star, the scale height of the atmosphere, which is more or less kind of proportional to the thickness of the atmosphere, and the temperature of the atmosphere, depends on the gravity of the planet. And most importantly, in this small parameter right here, that is the wavelength dependence of the spectral signatures, is the absorption coefficients of the present molecules. And this is where you get the composition of the planet, composition of the atmosphere. All right, so here we have the general idea of the problem. So here we have a transiting planet along in front of the face of the star. And during the observation, you get to see some spectra, right? We got that picture before. Now, if you are to employ a machine learning model, you're basically going to need to have a database. All machine learning models, artificial intelligence, or I would call that machine learning models, they thrive on data. They need a database that they can learn from. And that database, it could be generated either analytically through the formula, as we saw. You just plug in parameters of the planet, and you can calculate the spectra. So here is parameter of the planets. This is an example, very tiny database. Typically, those databases are of the order of 100,000 entries. So we're talking large databases. This is where the big data comes in. And it comes in as for example, input parameters. And you can use a analytical model to calculate, for example, the expected spectral features. So here's a table with, say, 4 wavelengths here shown only. For 4 different spectral beams, you can have those numbers, basically, what you see on the figure. Of course, this is very simplistic with an analytical model. So you can have a more sophisticated, by now quite sophisticated radiative transfer models, what we know as a forward radiative transfer model. One of those that is employed by the Ariel mission is the Tau-Rex model, but there are quite a few available on the market that do that calculation. They actually take a representative structure of the planet atmosphere, the temperature, the composition, they layer the atmosphere, say about 100 layers. They do full-blown forward radiative transfer calculation with given composition and given planetary parameter. These models will give you, will spit out a what is the expected observed value of the spectrum. Now, you could have also a machine learning model, and this is just a representation of a fully connected neural network, for example, that will learn from the available data sets and will find a mapping from the input and the outputs of the data to basically represent the model that created that data set, okay? So, and this is the idea for the forward model. Again, that computation can be done analytically with a full-blown radiative transfer model, forward radiative transfer model. And this is the first example of just giving you for the use of machine learning as a substitution of the fully developed forward radiative transfer model. The big key here is you need a large database for the model to learn. And your model is only as good as your database is. So one has to pay special attention how those databases are created, because the model can learn good or bad habits, depending on how you created the database. The same as children learn good or bad habits, depending on the parents they have, right? So this is the forward radiative transfer models or problems and the application of the machine learning for forward models. We do now inverse problem, which if you have not noticed, just inverses the problem, okay? So in the inverse problem, the planet model goes there, here's the spectra. We are answering the question, if I observe a particular spectrum, what is it that I can say about the properties of the planet? So this is your inverse problem. Before it was, I have my planet, I can calculate the spectra. Now, I have the spectra, what can I say about the planet? Those two databases inverted now, their locations. These are now the inputs, so known in the machine learning as features. And you have those different spectral values. In other words, this in a database. And the outputs would be the targets or the composition of the planet or the planet temperatures, radius, and so forth, okay? That can be done again through a fully blown inversion models. Typically nowadays is done through a Bayesian retrievals that results in the distribution, posterior distribution for those parameters, the likelihood of those, or the likelihood of their values. Or you can use a machine learning model that again finds a mapping of that database on the other database and learns these relations and is allowing you to find more or less the same answers as the fully developed inverse radiative transfer model. Pluses and minuses. The pluses are that these models are extremely fast, something that the radiative transfer models, the inverse radiative transfer models are lacking. So the hope is that the machine learning models will help us do those retrievals much faster. Okay, so let's go and see a few examples of the different techniques that can be used and something that we've done in our group. So we use supervised and also unsupervised learning. And I'll show you, actually we'll start with the symbolic learning right here in a few minutes. So you can use this variety of different learning, supervised, unsupervised, semi-supervised, symbolic learning, the reinforcement learning. This field is evolving remarkably fast. It is very difficult to stay in front of the development of this field. So there's new techniques that are showing up, but those are the things that we've tried in terms of machine learning. So for the supervised learning, what it means is you have both features and labels in the database. And the perfect example for supervised techniques is the one that we employed for the Ariel mission. This is where you have, for example, regression problems, where given the planetary parameters or stellar parameters, you predict the observed spectrum with this model. Those are typical supervised techniques. Categorization problems are also supervised techniques. This is something that we also have done. Now, unsupervised learning techniques, those are interesting because you have only features. You don't have labels for the learning. In other words, you are investigating your database, the properties of the database, and you have certain questions in mind. Is there any structure in that database? Is there any correlation between the parameters in that database? Are there any clustering in the database? Can I use some dimensionality reduction? What is the real dimension of my database? So all those questions are answered through unsupervised learning, and I'll show you a few examples in a minute. Oops, that's the wrong computer. All right, I will start with the one that I find is most intriguing, and this is the so-called symbolic regression. This is just a picture of having the AI acting as a theorist. Can we use the machine learning or the AI derive new theoretical conclusions out of the data? And I'll show an example of that. So again, the AI is thinking instead of us. This is in a more transparent way. I'll show you how that's employed. So in terms of the machine learning applied for exoplanets, we used a symbolic regression, which is here this square in this flow chart. So the symbolic regression is basically a package that is developed for trying to mimic a database using certain variables that the user is specifying, and tries to find a functional dependence that represents that data. In other words, trying to find a formula that will match the database given a set of variables. We want to derive the formula. In our case, going to be that formula that is hidden in the database. So this is kind of a discovery mode, applying machine learning in discovery mode. You have data, presumably a significant number of data points, and you want to find out what is the physics formula that would describe that data if you are able to specify certain variables that go into that model, okay? So the idea is, first you have to, we start with the atmospheric parameters, and for us, those are the temperature of the planet, the radius of the planet, the star radius, gravity, mean molecular mass of the atmosphere, and some composition of the atmosphere. Those are input parameters that we are using. Those are S right here and S right here. These are our independent variables. Those are the X, the Y, the Z that go into the formula. And this is one of the entries in the symbolic regression. On the other hand, we have those parameters creating spectra, either through a forward radiative transfer model, creates your database, that table that I showed you before. Or you can, for that, you can use a full radiative transfer model, or maybe, why not, an analytical formula to create that database, which is much faster, of course. What we did is we used the analytical formula to create the database, and we tried to recreate that formula as a proof of concept that can be done. And as a result, I'll show you what we have. So the symbolic regression, the package that we use, the PySer, uses actually tries to create a binary tree of the function of the function that mimics the database, and it returns different formulas that fit the data, and these different formulas have different complexity. So these are our independent variables, those pi's that you see here, pi 1, pi 2, pi 3, pi 4. Those are the independent variables that are the formula is a function of. And you can see how well those different complexities are fitting the formula. Here you have a graph of the error between, the residuals. The dashed line here just marks the parameter space where the model was learning, and the space outside this, the PySer has not looked at that one at all yet. It learns only in that region. So you can see that complexity 4, 5, and 8 are fitting very well in the region right here but it has deficiency when you have to extrapolate outside the region. So in the region of learning, does very well, but it doesn't do that well if you go outside the learning region. However, when it gets to complexity 9, that's much more complicated formula than those, it fits practically perfectly, not only within the learning region, but also outside this region. So the error here is basically machine learning, machine error 10 to the minus 15. So this is where we hit the exact expression of what it was used to create data, okay? So this is why I like that idea, because I mean, this was a proof of concept of applying machine learning or symbolic regression to learn the physics in that data. The next step is not having a synthetic database, but actual data, and try to learn what physics describes that data, okay? So I think that that's a very, very powerful tool to work in a discovery mode, finding new laws, new physics in our data. Okay, when we talk about data, this is the type of data that we are working with. These are examples of different databases that we worked on exoplanets. These are, most of them of the order of 100,000 individual spectra for a variety of planets. I'm not gonna go through all of them. Suffices to say that I will be talking about that one and show you some results. The biggest difference is one of those data, I mean, they both have about 100,000 spectra, but this one, as well as this one, is for a single planet. All parameter space scanned for that planet. This one is not for single planet. This is for variety, and I'll show you in a minute, for a large range of planetary parameters that are representative for what Ariel will be looking at. And of course, you can create your own database. So you can create whatever you want and then analyze it, okay? The first thing you can do is, this is an example of unsupervised learning, plain correlation analysis. How correlated is your database, the different parameters in your database. And this one is for one of the databases that you saw over there that shows high level of correlation between the individual wavelengths. These are the individual wavelengths, very high correlation between the individual wavelengths. What does that tell you? Well, the real dimension is not 13. The real dimension of that database is much smaller than that. You have much less independent information in those. So that actually motivates dimensionality reduction of your data. And then the PCA principal component analysis, that this is generally the idea of the principal component analysis. But from here, from the, depending how many of different principal components you include, how much is the explained variance in the data. And you can see that within the first 3 or 4 components, you basically captured all the information in your data. Why is that I like 2, 3, and 4? Well, maybe not that much 4. 2 and 3 and 1, 2, and 3 dimensions are very easy to visualize. If I can capture the information in my database within that many components, I can make pretty plots. I can show those pretty plots to you, right? So this same database that you saw in tables over there, you can represent in low dimensions, not in the 13 for the database that we used, or for the Ariel would be like 50 something dimensions, or for the JW that has many wavelengths, hundreds of dimensions. In 3 dimensions, you can see the clustering in that data. You can see compositional dependence. This is water, HCN, NH3, and the clouds. Each of those, so the watery atmosphere occupy this space in the principal components. The HCN occupies that space. The ammoniac occupies right here, and the clouds occupy this branch. So this is an example how a simple correlation analysis got our attention to decrease the number of dimensions, use the principal component analysis to capture the biggest variability in your data, and investigate dependencies with the planetary composition. This is a pretty video to watch with. You can appreciate the three-dimensional structure of your database. So it's very good to visualize your database to understand the main dependencies in there. All right, now we're going to talk about the Ariel database. Ariel, as I said, is going to have 1,000 planets to look at. They all look very different. This picture generated by the creative AI. What is it? I think it was called, yes, Imagine.com. This is what they used to generate that things, to generate that picture. Just the prompt was many exoplanets, and this is what it came up with. So what do we know what they look like? Not really, but these planets are actual planets. This generally captures the parameter of the planetary space that Ariel will be investigating. Right here, the different star and planetary parameters, those are real targets. Those targets are taken from the TESS mission. Those are actually intended planets to be observed. And as you can see, you have a variety of star and planet parameters. Here we have the radius, different radii, different temperatures. What is uniformly scanned is what we don't know, and that is precisely the composition of the planet. So in this data set, we have uniformly scanned water, CO2, CH, CH4, and ammonia, actually log uniform. I will be corrected right away. Okay, so we'll be investigating the behavior of the information in that database. Again, many different planets. So the thing that's actually also this, I'm going to talk about the latest work about novelty detections techniques for exoplanets. And this again to emphasize that machine learning is a tool, like any statistical tool. You really have to have the right question to ask in order to get the best benefits out of it. For example, everybody knows how to calculate standard deviation on the mean of the data, but what is the question that you're going to answer with that? The same thing with the machine learning. You have lots of different tools to use, but the important here is what is the questions that you're going to be asking with those tools and answering with those tools. So in terms of novelty detection for exoplanets, we are asking the questions, what if we observe a planet with an unexpected chemical composition? Are we going to be able to detect that? What if that spectrum has unusual physics? If it has unusual temperature profile, if it has unusual gravity, what if the instrument has glitches, mishaps during the observations? Or what if not detecting some alien life on that planet? Can we distinguish those spectra from the 1,000 spectra that we have available? How do we pinpoint, how do we spot interesting or unique, very unique exotic conditions on those planets? From a machine learning point of view, the question is, can we find anomalous samples in our data? So we're going to be using anomaly detection techniques. So anomaly detection techniques basically go in two categories. One is the outlier detections and novelty detection. We're particularly going to be using a novelty detection as an example, but just to make sure we understand the difference between outlier detection and novelty detection. So in both cases, we are actually asking the question, can we find a spectrum that is not typical? However, there's a fine difference. When you're looking for outlier detection, you have a database. This is your database. This is your training database. This is what your model looks at to learn. And you have typical examples and unusual example. Okay? So the model, while learning, learns what the atypical is. When you test your model, you test both on typical and atypical, and you hope that your model learned what typical and atypical is and can distinguish between them. This is called outlier detection. It can find the normal and the outlying samples in your data, but it has seen already, it has already seen what abnormal is. That implies that you know what the abnormal is, that you have an idea what it might look like. But what if you have absolutely no idea what the abnormal is? You have absolutely no idea what extraterrestrial life is, right? What to look for? Then this method would be not appropriate for your model. So then I'm gonna go with novelty detection. Now, note the difference. Now you're training on a database that has no abnormal data. It's everything that you see in the data is considered normal. And your model, your machine learning model that you use is trained only on those normal ones. Again, when you test on normal and abnormal, and you hope that it's going to show you that you may have correctly show you that you may have abnormal samples in your data. So for novelty detection, that means you have no idea what the novelty is. Can you detect the novelty? This is the novelty detection techniques. Now, outlier detections, there are quite a few different tools available for outlier detection. And that is particularly useful for fraud detection, fraud in the credit cards, security detection. This kind of methods are used a lot for security detection, fraud detection with machine learning techniques. Novelty detection, then we actually kind of struggle to find a variety of different methods to test. But as I show you in a minute, we found a few that actually work pretty well. So when are you going to be using those methods? You have to define what normal, what abnormal is. What is the white and black sheep looks like, right? So in order to define the normal and abnormal, we take our data. This is a histogram of the entire data. And we say, okay, we will consider normal atmosphere is an atmosphere that contains CO2, H2O, ammonia, and CO, but not CH4, no ammonia. Let's, for the purpose of the exercise, decide that this is what normal atmosphere looks like, no ammonia whatsoever. And then the abnormal would be the one that has ammonia. So this is the proof of concept that we have exploited in our exercise. So again, this would be the normal population, and this would be the abnormal population. We will train only on the normal, but when we try to see how good our model is, we'll be testing on a mixture of normals and abnormal spectra and see how it does, right? That's the idea. Okay, so we have done a few pre-processing steps. That's a very crucial step in machine learning technique, is to realize what is the best way to look at your data. And particularly for the spectra, we have done some renormalization of the data. This is just to visualize. This is a different spectra for atmospheres dominated by water, ammonia, and CH4. As you can see, they look very different after our renormalization, step 1 and step 2. The individual ammonia, CH4 atmospheres look pretty much the same as samples. This is the ammonia and this is the water. So this was the first pre-processing step that we did. And then we used, I'm sorry, wrong computer again. We tried to find different tools that are available. And the one that we tried to, you can see here, demonstration. This is basically taken directly from the scikit-learn that has these different tools available. Robust covariance, the one-class SVM model, this different version of the SVM, the support vector machines, the isolated forest, and the local outlier factor. And the ones that we use is that one and that one. And this is the results I will demonstrate here. Okay, so here are the results for, I think this actually for the experiment that we showed. And we have here the LOF, the local out factor method, and the one class SVM machine, the support vector machine. This is a test of how well separated the two population, normal and abnormal population, is during the analysis. And as you can see, you have very well separated populations of normal and abnormal test spectra. And we did that for different levels of noise. No noise, perfect, not surprisingly. some noise, 10 ppm, more noise, and even more noise. And you can see that as you increase the level of noise, the two populations start overlapping. The noisier it is, the more difficult it is to recognize a spectrum as normal or abnormal, okay? So this is the other method that we used, very well separated the two populations for the non-noise data, keeps being very well separated even with the increased noise. And here we start having more overlap between the two populations. But the overall observation is we have really good separation of normal and abnormal spectra. This is, I'm going to show you the ROC curve for those. This is just an example of what ROC curve is, or the ROC curve is basically a method to test how good is your classifier. What you want is, depending on where, this is a normal and abnormal population example. And this is basically a, let me stop somewhere. Oh, that's a bad place to stop. For example, here, how, if you draw a threshold, what's normal and what's abnormal, how well the two populations will be separated. The best ROC curve is if it goes like that. That would be perfect separation between normal and abnormal. Let's see what we got here. This is the resulting ROC curves for the support vector machines and for the local outlier factor here. This is for CH4, for NH3, for water and CO2. We had almost perfect for the support vector machine. Here, the ROC curves, almost perfect separation. And we had the worst separation we had for the CO2. That was, the two methods had more struggles separating the normal and abnormal spectrum. Nevertheless, with low levels of noise, you can see the support vector machine does pretty well. But however, the local outlier factor method struggled significantly when the noise has increased. So, amazing enough, I got to my final slide, which guys gives you the general takeaway points from this talk. And takeaway points are that transit spectroscopy for observing planets, it's a very high-dimensional problem, which works well with machine learning techniques. The high dimensionality cries basically for looking for ways to decrease the dimensionality of the database, because the lower the dimension, the easier it is for the method to perform better. And so these databases are generally highly correlated. Using the principal component analysis is a very good tool to see visualize the data in a lower dimension. I talked a little bit about symbolic regression. I find that very exciting method to find new and interesting physics laws or physics relationships in your data, basically directly working in discovery mode. And I find the anomaly detection techniques very promising in terms of finding the unusual and the unexpected in your database. And we're hoping maybe something very exciting in the observations of 1,000 extrasolar system planets with the Ariel. So with that, please have any questions.
Thank you, Katia. Other questions?
Nice talk, Katia. Thank you very much. Hi. My question is, did you try to use your symbolic regression method on in the frame of the PCA components? Like when you go back to your your figure, where you have a very nice and quite complex expression of clouds and water, etc.
Is that the one you're talking about?
No, the PCA figure.
Wait, it's coming.
The next one, yeah, this one. So would it be interesting to do a symbolic regression in that frame to find physical equation?
That is a very interesting question. Again, the PCA allows you to look in lower dimension, which it is generally the machine learning methods have easier time when you decrease dimensionality. Now, that's not an exception also for the symbolic regression. For us to decrease dimensionality, first we performed a dimensional analysis, and we formed, I skipped that very essential part because it was too much of a detail. What we did is, let me show that. What we did is these pies over there, these were actually dimensionless groups that were formed from the variables in the problem. So instead of working with 8, 9 dimensions in terms of variables, we worked only with 4 dimensions by performing, but we decreased dimensionality of the problem by basically performing dimensional analysis. We form dimensionless groups. Rather than temperature, we have temperature divided by the stellar temperature. Or instead of scale height, we have scale height divided by the radius. So we have combinations of those physics parameters in dimensionless groups that decrease the dimensionality of the problem. We have not tried to go to the PCA in PCA space, but we are giving you what our group is currently working on. It's not published yet, but we're working on autoencoders to decrease the dimensionality and see the physics dependencies with autoencoders.
Another question?
No alien questions?
Maybe there are questions on Zoom? No?
Anybody questions on Zoom? No?
No question.
Okay. Well, all those things that I showed, they're published already. So feel free to go and dig in some more details if you have more questions, because I clearly did not go into great detail in any of those topics. Well, thank you very much for having me here and for having your attention here for a whole hour. Thanks again.
Thank you.
Thank you very much. So Katia will be here all day long, right? So if you want to maybe to have a chat, Katia will be at the Institute.
We will be mostly at the forum at the second floor if you want to meet us.
Yeah. How to apply it, but it's useful for your problem. Again, all those tools that I showed today, we apply them in this particular field of exoplanets, but all those things are applicable for any of other scientific problems. So if somebody is interested and wants to know how you can apply those things, feel free to talk.
Thank you, Katia. So at the forum.